Hello, next speaker, Richard. All good? Ready?
Yes.
Let's talk about ZK and Zupass.
Yes, we'll talk about
Let's do
ZK
it.
and Zupass. So, good afternoon, everyone. I'm Richard. This is Ivan. We contribute to the Zupass project, which is an open source ZK experimental tech. If you've noticed, your ticket has been in Zupass when you checked in, and in here we'll go a bit more over how do you actually use this technology to build your own apps, right? In here we'll learn a bit about how to create ZK proofs with under 20 lines of code, even if you don't have too much ZK specific background. So without further ado, we'll begin, and actually I'll hand it off to Ivan to do a bit of an intro as well.
Hello. I'm not going to be doing the workshop. I'm just sort of here to introduce myself. If you need help with any of the stuff we're going to present, or Richard's going to present, I will be in the back after the workshop and available on the internet as well.
Cool, thanks Ivan. So again, these are your tickets. They contain the tickets you need for registration, but what can they do beyond that, right? Well, I think some 200 or so folks have joined the Telegram, and in the Telegram what you need to do is talk to a Telegram bot, this bot ZKat. It's a friendly bot that manages zero-knowledge proofs. And in here, you have a screen where you have to prove that you own a ETHPrague ticket in order to join. So for folks that are somewhat familiar with that flow, you've already used a ZK proof. In addition, and this was announced a bit at the opening ceremony in the hacker manual, but the Zoo poll, or anonymous vote, the hackers and audience vote on Sunday. So after everyone submits, everyone's going to vote for projects. That will also be through making a ZK proof for your Zupass, and that essentially is sort of so we can have anonymous voting, so you don't have people sort of like bribing each other to see, who voted on which. So these are two sort of examples of ways within the conference how Zupass and ZK authentication is used. So we have this common kind of screen here, right, of some kind of, okay, I have a piece of data, in this case my ETHPrague ticket, and I'm making a ZK proof out of it, right? This is sort of, you can think of it roughly analogous to a MetaMask confirmation screen, right? You're signing a transaction, in this case you're making a ZK proof. And in this ZK proof, I'm revealing two things in my ticket. I'm revealing my email and my name. In other ZK proofs, I'm revealing other things. For example, in Zoo poll, I'm not revealing my email or my name. I'm revealing a specific ID or nullifier that indicates that I'm part of this sort of Merkle group of the event. So I can go more into the details of that later, but just know that this screen represents different kinds of proofs, and you can see sort of within the screen what exactly you are revealing in each of these proofs. So you might be thinking, well, okay, this ZK stuff is cool and all, but isn't it super hard? Isn't it like moon math? Don't I need to be some kind of like academic to get started? So this is, here is a language called Circom. It's pretty complicated. It's actually like one of the easier of the ZK languages that people use. And essentially it consists of writing code as math problems, right? So this is like a pretty fun, interesting challenge, but it's not really convenient when you have like 2 or 3 days to hack on something useful, right? Or if you just want to get started on ZK for the first time. So although we love Circom, we think that Circom is probably too inaccessible to most developers. So we developed this library, this open source library called ZooAuth. And everything you need to request a ZK proof is contained within the lines here, right? So there's this one function, await ZooAuth pop-up. In here, you request, okay, I want the user to reveal their email, their name, and the event ID, the fact that it's ETHPrague. I can optionally submit some kind of watermark to commit to some sort of message, and I'm saying that I'm using the ETHPrague tickets configuration, right? So this is like less than 10 lines of code to request a ZK proof. Okay, so that's a bit of a preview of what's going on. Again, we have Zupass during the event. We have a bunch of different apps that request ZK proofs. Creating your own ZK app can be super, super simple. Doesn't require any knowledge of math or deep ZK expertise. So I'm going to do a bit of a briefing of what is Zupass, what is the sort of actual architecture of it. So one decision for Zupass is that data is held locally on the device. So rather than it being stored in plain text on a centralized server, which is typical of things like Facebook or like large companies that have these apps, data is held locally in the device, and we store an end-to-end encrypted copy so that you can log into your Zupass on different devices or on your laptop and your phone. The data that's being exchanged is client to client, right? So if you remember in those examples, you had Zupass talking to the Telegram bot, right? Or you had Zupass talking to Zupoll, or Zupass talking to some ZK app of your choice that you hack on in ETHPrague. The data is being exchanged between the Zupass client and that app's client. There's no sort of like big server doing all that computation. And because of this, ZK proofs ensure privacy and data integrity. Right? There's no need to trust a centralized server. The clients can just verify that the proofs are valid. So you can kind of see that this is very analogous to what, like, some of these ideas are pretty related to what working on Ethereum enables, right? Except to work on this, you actually don't need to like hook on chain. You don't need to set up like an RPC to infer or anything, right? You can just get started with those 10 lines of code, and that's kind of what is the breakthrough here, right? Like we can start hacking on ZK proofs without needing to do all this setup. We do have some exciting like on-chain integrations though for folks that want to get more into it towards the end. Specifically, like how do you verify ZK proof on-chain? Cool. So, okay, that was a text-heavy slide just to give another sort of analogy of what's going on here. This was the setup we had, like one setup we had at DevConnect. So we had a developer from the Ethereum Foundation, Philip, who built this Holisky. Holisky is also the name of the city, right? But Holisky is a testnet as well, and that they have a faucet that issues testnet ETH for developers. So if you proved ownership of a DevConnect ticket, right? There's that proof screen over there. You're revealing your event, your sort of Zupass specific public key. Then you can log in with Zupass. The faucet will authenticate you, and then it will, after you're authenticated, after you're validated, it will send you that 500 whole ETH. So essentially, you had an app that was gated to having like been to DevConnect, right? You can imagine like adding complexity into this, right? Like for example, this app is. You have to prove that you have a DevConnect ticket and get some ETH. You could add on like, prove that you had a DevConnect ticket and you checked in, right, and then get something else. Or prove that you have a DevConnect ticket and you have an ETHPrague ticket, right, and maybe get like 700 whole ETH. Or sort of arbitrary predicates can be expressed through many of these like proof screens. So what actually happens during this process of authentication? So the first thing that happens is, well, you request a certain kind of proof. So that's the different parameters on the screen here, right? You request what, in this case, this specific proof, ZK event ticket PCD. It's kind of a mouthful, but it's requesting these two fields from you, email and name. And then after this proof is, after the user clicks prove, that proof is then sent to another client or server, really anywhere that you want, and that ZK proof is verified. So essentially what's going on is you have an app that's, again, requesting a proof from your Zupass, and that the proof is being sent to a different app, which is verifying that ZK proof. Maybe I'll go to the following slide. Yeah, so verification. Again, proofs are verifiable. You don't need to trust any sort of third-party API. And it's cryptographic verification. So you can check the content of the actual data itself. Cool. I'll just probably stay here, actually. So there's one other thing, if you remember on that first screen of the 10 lines of code, which is the watermark. So some proofs can contain an arbitrary watermark, which is kind of similar to like a challenge in the Web 2 world, right? Which is, or like a nonce in Ethereum, right? Where you, let's say you want to avoid man-in-the-middle attacks, you can have the client sign a certain watermark. You can have like client number 2 or a server check that same watermark, and that way you can prevent somebody from sort of like, who might intercept that request from, interfering with this authentication. Yeah, and it also allows for credential replay attacks. So one thing you can do is put a timestamp in the watermark. Cool, so going back to this screen, again, we have the process of requesting a ZK proof through Zupass, and the verification is actually even simpler. You just need to call this authenticate function, and in here you post the actual, PCD string, PCD str, which is in this result here, towards the bottom. And then you place your watermark, and then finally the configuration. So again, having that watermark be the same, that watermark needs to match the watermark that you request in the client in order for this authenticate function to verify properly. Otherwise, it'll throw an error. Okay, so we're moving pretty fast here, but one extension of this, again, here we're mostly talking about, this is all TypeScript again, so you can run it in the front end, run it in a node server in the back end. But what if we want to do something on-chain, right? For example, there might be smart contracts that have that want to sort of verify ZK proofs of, anything from as small as ETHPrague attendance to in the future, right? Verifying, government IDs, right, or like financial records. So I think getting ZK verification on chain is a pretty exciting primitive. And here's this QR code for a library that Austin Griffith from Bill Guild hacked on, which is essentially, and you can kind of see in this diagram here what this process is. Maybe I'll actually show the video first. That'll give a better idea. Cool, so I'm gonna full screen this. So we have a Zupass scaffold ETH2 starter kit. And one note is that I think this is, ETH Berlin tickets, but the principles are mostly the same besides that. So the first step is we request the ZK proof, right? So in this case, it opens a pop-up requesting from our Zupass an ETH Berlin ticket. In this case, I have an ETH Berlin hacker ticket. And it's requesting my email, the event, and the product IDs. So I go ahead and click prove, or I have 2 tickets actually. I can choose the hacker ticket. I click prove, and then I can, because we're going a bit fast here, I can verify first on the front end, because there's that node TypeScript library I can verify within this React app here. I then verify in the back end, and then after this, I send this to a server, and then I verify that within a server using that same authenticate function. And then I send 1 ETH to the address I'm connected to. And then finally, the step 4 is sending the proof to a smart contract. And this smart contract takes that proof and verifies the proof on chain by doing some like math operations essentially. Specifically, it's like it's a Groth16 verification, but it verifies this, and after doing so, mints an NFT for the user. So if we go ahead and click on the sample block explorer, we'll see that the latest transaction is like a mint item to the account we're connected to. And if you're curious, the watermark we mentioned from earlier was used to encode the address that I wanted to mint that NFT to. And that way that prevents, it's like I'm committing to, okay, I want this person to be minted an NFT to prevent sort of, fraudulent transactions. Okay, so just to go over this again, we have the scaffold ETH2 front end, which is, everything you saw, on the web page. The first step is requesting a proof from Zupass. Your data is stored locally in Zupass. It sends the data back to the scaffold ETH front end, where it's verified. That's the step 2 here. Step 3, it sends the PCD, the PCD is sort of the name for the ZK proof, sends the PCD to the backend of scaffold ETH, where it verifies the proof and sends the ETH, returns a 200 response, and finally it sends the proof on chain where it's verified in this kind of big smart contract, where it calls groth16 verifier.verify proof, and finally mints the NFT. So one way to request a proof from Zupass, and 3 different ways to verify it on the front end, on a server, and on chain. And yeah, all the code here, you can look through some of the examples to get a sense of what's going on here. And Ivan and I are also happy to help walk through any of the details. Oops. OK. So that mostly concludes the workshop. Again, the kind of key thing here is Zupass is software for for easily requesting and verifying ZK proofs. You can create a ZK proof by writing these 10 lines of code by using this Zupass pop-up on the client, and you can verify it with an authenticate request. We also have some libraries for on-chain verification. And we have a sort of complete list of documentation for developers at this QR code here if you're more curious. We also, lastly, have a Telegram group where you can ask questions to some of the other Zupass contributors from around the world, and they can help out in debugging the issues, helping you guys create a great hack. But yeah, that's mostly it. Yeah. Thank you all, and
Thank you.
We'll take any questions.
Thank you, Richard. Any questions?
Thanks. I love it. I think ETHPrague last year we gave out some SBTs on like a QR code. It was really rudimentary, and I hated it at the time. And it's wonderful to see this year. It runs really smooth. Yeah, in fact, there's so many more applications for this, right? It's a much more general product than just authentication for getting into spaces, for example. Could you explore that a little bit, and what are you thinking in mind on the more generalized set of use cases in this?
Yeah, great question. So there's actually a lot of prior talks about the more kind of like expansive direction. So I work for this organization called ETHPrague that focuses a lot on this field called programmable cryptography, which is essentially what are the new sort of possibilities that this essentially really powerful technology brings us, right? And Zupass is just really the tip of the iceberg. Authenticating tickets is just really the tip of the iceberg, right? So to go into that a bit, I think that you have, maybe I'll just sort of give a bit of a prelude and direct folks to watch some videos afterwards, but we have this world where we're moving from first generation cryptography, which is things like signatures, encryption, to second generation cryptography, which is ZK proofs, and even more complex cryptography such as multi-party computation, fully homomorphic encryption, a lot of these like buzzwords that you might have heard of. And the powerful thing about this is that, well, one, a lot of these protocols that were in first generation cryptography, right, were mostly about like defense, right? It's like, I want to secure my data so that hackers can't exploit it, right? Or I want to keep certain things private. I want to communicate only with certain trusted parties. Or I want to verify, or I want to show that this piece of data is signed by me, right? And nobody else can claim that. This category of second generation cryptography actually allows for a lot more like kind of offensive, like new things to be created as a virtue of things being like hard, right? So I think blockchains are really the first, like a good example of this, right? Where you have, some ecosystem like DeFi emerging because all these contracts are composable, right? And like the sort of, like coefficient of creating a new application is super, super low, right? I think with ZK proofs, we're seeing a similar sort of thing happening for like existing data, right? So a lot of data exists out there in financial records, governments, right? That can be, sort of signed and then created, shared between different entities, right? Like the world that one could imagine is one where you store all your data locally and you generate proofs of that data to certain, like consumers of that data. So like, I don't need to sort of have an Equifax score. I just store all that data locally in something like probably a lot more complex than Zupass, right? And then anybody can sort of request some sort of part of that data. It's almost like a global API, right? Without needing to conform to all these like very specific specs that we have in the current world. So I'll kind of close off with directing folks, if they're curious, to see Gubsheep's talk at Prague Crypto about programmable cryptography. So you can search this on Google, and that will give like a much broader view and more detailed view into what this world leads to.
Any other questions? No? Silence. Thank you.
Cool.